And then let's see. Fabulous. I think we're ready to roll now. So welcome everybody to the kind of restart of the Monsoon seminar series for this year. For those of you familiar with what we do and those of you unfamiliar with what we do, this is just an informal online seminar series in which we talk about some of our passions, including the monsoon and its evolution through time. So without further ado, I would like to introduce our speaker. Our speaker for today is Dr. Pawan Govil, who is a scientist working at the Birbal Sahni Institute of Paleosciences in Lucknow, India. He completed his master's, in geology from the Aligarh Muslim University and his PhD from the National Institute of Oceanography in Goa. His main research includes the application of platonic foraminiferal methods using stable isotopes and biogeochemical elemental ratios to understand glacial interglacial cycles and the evaporation precipitation budget, all in context to climate variability. And so before we let our speaker begin for today, please type your questions into the chat, and then at the very end of the talk, we can call on you to ask your question out loud, or I can read it out for you. And so thank you very much. And we can put our digital hands together to welcome our speaker, Dr. Pawan Govil. Thank you.
Thank you, Dr. Tara. Myself, Pawan Govil, as she has already introduced me. And I'm very much thankful to Dr. Tara, Professor Peter, Professor Livio Jensen, to start this monsoon series, and each and everyone can share their views there. So I'm really very thankful to you and for the invitation and all. So thank you. I just would like to start with my talk today is understanding the Indian monsoon with proxy records from the Northern Indian Ocean. So today's content of the talk, first just have an introductory Indian monsoon system, summer and winter, present hydrography of the Northern Indian Ocean, in which we can give some time to SSG, SSS and circulation pattern, sea surface temperature, sea surface salinity and circulation pattern. Monsoon and proxies of Northern Indian Ocean, what we usually use to decipher the monsoon intensity over the time period and how to do it. And so in that, I would be taking by the time period. First, glacial, interglacial monsoon and variability, and then Holocene monsoon and variations, and their inferences, if we have any. So I just would like to give introductory summer monsoon, like when the temperature and the pressure gradient between 30 degrees south to 30 degrees north in the from Madagascar to Tibetan Plateau during the summertime period. So it generates lots of precipitation and air or the wind circulate circulate from the ocean to the land, and the intensity of the wind is very high during the southwest monsoon, so which brings lots of moisture to the land and precipitate there. So in this way, we go for it is really helpful for us because we are agriculture country and so on. So it is very good for us to have the good monsoon. And then the precipitation is over the 90% during this time period in 4 months, June to October, 4 to 5 months. Reversal happens in the winter monsoon, cooling of the land, wind with the reverse wind direction from the Tibetan Plateau to the ocean, and it is a dry, cool, dry winds. So, and not that usually we say it's a northeasterly winds, which is from the December to March, and we get very low precipitation there. So I would like to talk about present sea surface temperature, salinity, and circulation in Arabian Sea and Bay of Bengal. Just so in this, we have, I'm showing here that average sea surface temperature in the northern Indian Ocean during the southwest monsoon. It is very unique features in our northern Indian Ocean, in Arabian Sea and in the Bay of Bengal, that high SST gradient is there in the Arabian Sea compared to low gradient SST or low SST gradient in the Bay of Bengal. In the northeast monsoon, the same thing, that average sea surface temperature, high SST gradient in the Arabian Sea and low SST gradient in the Bay of Bengal. But in contrast, we have a very high salinity variations in the Bay of Bengal rather than in Arabian Sea, because we have so many rivers there, Ganges, Brahmaputras, Irrawaddy, Mahanadi, Krishna Godavari. So much water influx is there, which makes salinity to go down. So sea surface salinity gradient is quite high in both the periods, in both the monsoon and Bay of Bengal compared to Arabian Sea. So again, I just would like to say about the Indian Ocean circulation pattern. In Indian Ocean circulation pattern during the summer time, WICC, Western Indian Coastal Current, takes a high salinity water into the Bay of Bengal, and Indonesian through flow, which is you can see here, and then it mixes up with the it converted into southeast Madagascar current and northeast Madagascar current, and then East African coastal current, and then goes up in SEC's South Equatorial current, and comes to the Western Arabian Sea. Just opposite happens in the northeast monsoon, where we have seen the Eastern Indian coastal current with the low salinity water enters into the Arabian Sea and mix up with the WICC. And the current from ITF to NEME, NEMC, and EACC, which makes a loop there. So these in monsoon, we have to understand the circulation pattern. So how they are working and how they are transferring the heat or cold signatures to every basin. So just I would like to give a brief that monsoonal proxies of Northern Indian Ocean. Basically, there are many proxies which we can use, and everybody use different proxies. But basically, I work on foraminifera because they are very sensitive to the marine system, and they have all the signatures, so they are very sensitive. And so I work on the foraminifera senses and assemblages, in which relative abundance of planktonic foraminifera or the individual species. And then second, geochemical and isotopic signature of those planktonic foraminifera shell. Basically, we work on species-specific results we have to take. Stable isotopes of carbon, oxygen, elemental concentration ratios. And then we come to the geochemical and isotopic signatures of bulk sediment for carbonate mineralogy, particle size analyzer, stable isotope of organic carbon and nitrogen, and trace element concentration. And then later on, we can talk about a little bit about the periodicity in our area, or wavelet, etc. So I'm just going to start about the proxies what I have used the most. I'm working on planktonic foraminifera. I work on Geranoid super. This is the water column habitat, 50 centimeter. I have used this size fraction for oxygen isotope or magnesium, calcium, or boron isotope measurement. Before going to the talk, just I would like to say that what kind of signature it keeps. And it is really very important to understand that oxygen isotope ratio. Each and every proxy have their controlling factors, but oxygen isotope ratio is very much important for us to understand what it keeps in it. So delta routine of calcite is basically depends on three things: temperature and salinity, but in salinity, global salinity and the regional salinity. So delta routine of seawater plus temperature, and if you change into global salinity and the regional salinity, then global salinity, that volume we get delta ice volume plus local salinity effect, and then the temperature effect. Independent SSC estimation by magnesium calcium ratio. So once we do the independent temperature estimation, then we can infer up to the past sea surface salinity. We can get thread by thread, we can get the very good understanding of the evaporation precipitation budget in the area. And then we have recently we have done a boron isotope for the estimation of pH and CO2 of the ocean. So these are the locations on which the core locations from the marine area on which I have worked in northern Indian Ocean from Arabian Sea and Bengal. So as I said earlier, that I am going to talk about first glacial interglacial monsoonal variation, and then the second topic I will take up Hodocene monsoon variation. So in this, I am going to start first from the one of the core from the Western Arabian Sea, BM3504PC. So this present study, we have used oxygen and carbon isotope to reconstruct the monsoonal variation up to the M-6. But before going to that, I just would like to say that this core is from the Abelling area. So we can just understand what is Abelling. Abelling is when high intensity wind action is there in the Western Arabian Sea, so it wash off the surface circulation, and from the deep, the cold and nutrient-rich water comes up. So that's what with the Atman transport, it happens Abelling, and it increase the productivity but lower the sea surface temperature. As I said earlier, lower the sea surface temperature in Western Arabian Sea, and that is what we have high SST gradient in the Arabian Sea rather than in Bay of Bengal. So in Western Arabian Sea, I just would like to take you to some of my results. That with the on the x-axis we can see the age, and the y y-axis we can see the data set. So with the LR04 landscape data set, we have correlated our core for the chronological purposes, and then with the this is our data set in red, and this core goes up to 172 kilo year. In the red, it is a delta weighting of calcite. In the green here, it is basically when you correct the ice volume, continental ice volume correction. So the gap between this delta weighting of residual and delta weighting of calcite, it tells us about our sea level variation during the glacial time periods. Dark band here, they show the glacial periods, and the white one, the left one, they are called interglacial periods. So we can clearly say that during the glacial periods, Indian summer monsoon intensity was lower, and in the interglacial period it was higher. So it changed the whole hydrography of that area, and that is what we get the signature in these kind of studies by the isotopic studies on foraminifera species specific. So apart from that, because LR04 is from the benthic foraminifera results, so we have taken one core from the Eastern Equatorial Ocean, and we have compare our results with that. And delta carbon 13 basically tells us about the nutrient availability or the chlorophyll there or the productivity there in the ocean. So in the glacial time period, the productivity is low, but in the interglacial time period, the productivity is high. And we have, this is very interesting results we are having now. We have started to work on this core from last 2 years. So there with the equatorial Indian Ocean and with the southwestern equatorial Indian Ocean, we have compared our results. And one thing is very peculiar in our results, that we have mid-MIS4 warming, which is supposed to be a glacial period or the cold period. But in Western Arabian Sea, we are seeing that it is a warming is showing. So that warming basically, because it looks like it is regional, because I mean, if you see all the data set here, they all are showing that during the MIS4 from the Bay of Bengal or from the equatorial Indian Ocean or from the southwestern equatorial Indian Ocean, they all are showing that it is showing the cold period. So in our area, if it is showing warming, then it must be a regional phenomena. And during that time period, I believe that southwest monsoon and the northeast monsoon both were coupled, and because of that only we have received this warming there, and it stops merely the or decrease the circulation of the low high salinity water from the Gulf of Aden and the Red Sea. But if you see those records, even in our planktonic foraminifera assemblages, where we use the gloids as a Belling indicator species, then also it is showing during the MIS4 that the upwelling happened there, which is very unusual, because in the cold time period you have northeast wind intensity and upwelling does not happen. Like in MIS6, there is very minimal according to the results. So like that, whenever the upwelling is happening, then glutenata, rubescens, or fertile species even showing their abundance high during this MIS4 event. So geobloids and G-Rupert ratios is also saying that the vertical mixing was there or the upwelling. So we have seen our results with the insulation part, and I mean comparative with the insulation part, and during the MIS6 we can see clearly that it is very much coherent, and even MIS5, and in MIS4 this is a peak which is going from lower insulation to higher insulation. Maybe this may give a cause. If you see the geobloids pattern in the MIS4, then I think it is related to the insulation which drives the warming there in that Western Arabian Sea. Second, I would like to talk about other cores, glacial interglacial monsoon variability from Eastern Arabian Sea and Western Bay Bengal core, in which we can see that one core EAS 9/21, and we can see that Narmada, Tapti, Indus rivers are there to give the input of freshwater flow to the Arabian Sea. And second hand, we can see the Krishna, Godavari, Mahanadi, Ganga, Brahmaputra. They are pouring their water into the Bay of Bengal, and there we are going to talk about SK21A by 1. It's a port site in Western Bay of Bengal. So first I will start with the Arabian Sea delta wetting of seawater. This data set we have taken from the Jacobs study by Dahl and Oppo et al. 2006 and presented in Govil in 2010. Where you can see that in the coastal area we have 0.4, and in open ocean we have 0.6 value of the delta wetting of seawater, in which this planktonic foraminifera lives. So they have those signature in it. Particularly comparatively, if we see, then Bay of Bengal delta wetting of seawater is pretty lower. I mean, or I can say that from the negative excursion, that it is from the minus 0.54 to they come up to 0.36 or 0.42 in the southern part of the Bay of Bengal. So this Bay of Bengal water is more lighter than Arabian Sea. So I just would like to talk about first about the Eastern Arabian Sea floor, where again the delta weighting of calcite, and we have removed the ice volume history from there. So this is the delta weighting of residual, which tells us about the sea level variation in it. And our core is very well versed with the delta weighting of calcite with mosaic work within the Arabian Sea. Secondly, I would like to talk about that we have reconstructed the SST based on the magnesium calcium ratios. And we can see very clearly that during the MIS4, we have, in this data set, we have quite warming there compared to MIS3. And it is not, MIS4 is not as much as cold what MIS2 is there. And definitely in MIS1, we have the higher temperature, and the whole core variation, the core temperature comes up to 29 degree to 24.5 degrees centigrade variation. So 4.5 degrees centigrade or 4 degrees centigrade variation we have from LGM to Holocene. Apart from that, we have seen it is very unusual. It was very unusual to see that we have two warming periods in Eastern Arabian Sea records, and we have compare our results with other SST data set from the Arabian Sea, from the Western Arabian Sea, and from the Eastern Arabian Sea, and from the Southeastern Arabian Sea. So we have seen that similarly they have also captured this warming. So this warming basically is first of all, it was noted down in the Sahara and with the 911 bin in 1985 and Sahara 2007. So they have given the reason that it is a heat flux during the LGM time period, which has come with the water or the ocean circulation is responsible for it from the northeast Madagascar current to southeast equatorial current, and then it has given a heat flow or heat flux transferred to the Eastern Arabian Sea. So later on, we have seen the same, definitely the same warming event in the delta weighting of seawater, because once we get the temperature, then you can subtract the temperature effect from the delta weighting of residual. And then we get the delta weighting of seawater, and then from delta weighting of seawater, you can convert into the salinity. So we can see that during those two warming period, it is quite unusual again that the salinity was a little bit high. At the same time, it is from the SK17 report also, it is measured that during that time period, the salinity was delta weighting of seawater values were a little bit higher. I will give you the reason later on. Just I would like to show, because same kind of phenomena or same kind of results we have got in the Western Bay of Bengal. So in Western Bay of Bengal, we have this again the delta weighting of calcite, and then we have reconstruct the delta weighting of residual. Then in the Bay of Bengal also, which is which doesn't come under the upwelling area, Eastern Arabian Sea and Western Bay of Bengal, but still we have there two warm periods, and during YD also we have temperature down, and during this time period, if you see the delta weighting of seawater value, then they are little bit high. It is unusual because salinity should be low during that time period. So it is because that during the northeast monsoon intensity so high in the LGM time period, but it has the precipitation by the northeast monsoon intensity or by the southwest monsoon intensity, it was low. I mean, both the monsoon intensity was not up to the limit to provide that much freshwater influx to the area. and that is what it has been noted down as a high salinity there. And we have compared this result with our Andaman Ocean also, Andaman Sea results also, and we have the same signature from there. So I was just thinking that for this job, I was just thinking that we can just compare these things, because according to me, or according to what we have seen in the present sea surface salinity, sea surface temperature from the Bay of Bengal and Arabian Sea. So we have seen that the temperature differences there, salinity differences there in both the basins, being on the same latitudinal lines. But I have seen in this result, that's what I did the comparison of only just two basins data set. So if you see that during the MIS1, there is a variation in the SST in both the basins, which can be understand. But at the same time, in MIS2, if you see that apart from they are on the same latitude, differences should be there in the temperature and salinity reconstruction, but they are same. I mean, the temperature is almost same in both the basin during LGM time period. So, and when we compare with the delta weighting of seawater results from both the basins, again, the difference of delta weighting of seawater in both the basins are really much. But during the time period of LGM, it is not differing at all. I mean, they are very much same. So this is saying that during the northeast monsoon intensity, during the LGM, you have low saline water enters into the Eastern Arabian Sea. Now I would like to talk about the Holocene records, what we have working on, and reconstruction of Holocene climate and oceanography using Arabian Sea and sediment cores. Study of productivity, southwest monsoon, sea level since Silver Dry. So these are two cores in which I'm going to particularly talk about SK240 485 core. So in this core, first, the same, I have taken the longitudinal Zuber to attain the delta 18 data set, oxygen iso data set, and the higher the value means lower the value in the negative excursion, it shows wet period, and the higher the values, they show that result shows the dry period. So during the YD, we can see clearly that dry period was there, and it was not much precipitation happened there. And during the pre-boreal, yes, again warming happens. So we have almost very high resolution data set on it, and many abrupt climate variations are there. 8.2 kilo year event is there, 4 kilo year or 4.2 kilo year event is there. So basically what I have seen in this result, that it is quite from Pleistocene Holocene boundary to 1 kilo year. It is a freshening trend, which we can see in the delta weighting data set. Secondly, I have done some planktonic foraminiferal assemblage or planktonic foraminiferal abundant data set, benthic foraminiferal assemblage data set, P by B ratio, and the delta carbon 13. Delta carbon 13 again shows that during the dry period you have less productivity, and during the wet period you have a little bit high productivity. And in this area, we have seen the planktonic foraminiferal abundance, which is showing that it was very less. So why it is? Because during this time period, our sea level in the western coast, it was coming up, and this whole site is from the 88-meter water depth. And during this time period, during the YD time period, and above that up to Hurley Holocene, the sea level was down by 40 to 50 meters. So that is what, if you have I mean, if I see that the core site is from 88 meter now, then during the during the Pleistocene Holocene boundary and during the early Holocene, it was more or less 40 or 40 to 50 meter. So planktonic foraminifera was not much flourished. Then the same thing with benthic, and it is slightly planktonic PFA. If you see that it is almost goes with the delta 18 data set, it is increasing up to 1 kilo a year. And we have seen we can see the calcium carbonate data set, which is showing very high. It is because of the aragonetic deposition on the core site during the Pleistocene Holocene boundary or in the early Holocene. We have that record with us, but I have not shown here. And at the same time, in this benthic foraminifera and planktic foraminifera record, if you see that we have measured or we have seen high sea level maxima during 5.5 kilo a year. On this score, we have worked to understand the PCO2 variation in the northeastern Arabian Sea, whether the area works as a sink or source to the PCO2. So we have done the foraminifera magnesium, calcium, and boron isotope study from northeastern Arabian Sea for SA 240, 485. So in which first we have generated the magnesium calcium data set, and before I'll go into detail, but this data set we have generated from University of Southampton, UK, from working with Gavin Foster. So in the Foster laboratory. So SST almost within the 8 kilo a year to 1 kilo a year, SST shows 3 degree centigrade variation within the Holocene. And then we got the delta 18 of seawater we have calculated, and it shows the freshening from 8 kilo a year to 1 kilo a year in the area. Delta boron 11, it shows 19.8 to 21.8 per mil difference, and pH scale shows the 8.05 there, 8.05, almost average. Average is 8.12 somewhere, and this is the present actually pH. And then we have calculated the PCO2 of seawater, and then the delta PCO2, where it is the difference between the atmosphere and the seawater PCO2. So remarkably, or it's a little bit unusual, but we have got there two very high intensity CO2 basin have worked as a CO2 source. So this is nearly around 4.4 kilo a year, and one more point is there in 2.2 kilo a year. And we have compared our result with the data set from the Atlantic, Pacific, from the ice core, and in the Indian Ocean, in the Eastern Arabian Sea. We are the third one to work on, and before we got this NIUP 464 and EAS 9/21, which have been done by this NIU group. So the data shows very clearly that this abrupt CO2 outgassing that happened. So the same kind of data set we have from the Atlantic during 4 kilo a year, and it is because of the upwelling. And even in the Pacific, we have this kind of data set. Whenever this CO2 outgassing happening, it is either because of too much vertical mixing or because of the upwelling in the area in certain time period. So that is what our results suggested, that even in a very coastal area, we have this upwelling once in a while. I mean, that is very unusual, but it has the PCO2 working as a the area is working as a source on 2 episodes. Otherwise, it has worked as a sink from 8 kilo a year to 1 kilo a year. So there we were thinking that what can be the reason why it is happening. So we have compared with the ANSO activity data set, and it shows that during the time period upwelling happened just because of we have the ANSO activity, and then it triggers the upwelling in our area. So that is what we have seen. IPCO2 episodes are also quite strong acidification in the area. Now I would like to talk about the Bay of Bengal core from SK336 by 3 Western Northwestern Bay of Bengal core reconstruction of Holocene. So just I am coming to the interrelation to the Holocene end now in 6,000 years. So there we have lots of very abrupt changes in the hydrography of the surface hydrography of the northern, Western Bay of Bengal. So from 5.5 kilo a year to 4 kilo a year, we have aridification kind of, or the dry. It is becoming dry, but just for 500 years it was stable. Otherwise, from 5 kilo a year to 4 kilo a year, it is a dry state. And then step by step, if you see the data set of delta 13, then you will see that it step by step, it is going to it is going in the wet phase or in the normal phase. And we have got Roman warm period and medieval warm period also we have noticed in our core. So during this time period, during medieval warm period, we have more freshening to the Western Bay of Bengal compared to Roman warm period. So we have done this sand percentage or planktonic foraminifera abundance, benthic foraminifera abundance, and you can see that during the MWP and the RWP there are considerable changes are there in this data set. P by B ratio. It is also showing few changes there in the MWP to RWP, and then we have done this planktonic foraminifera assemblage. We have seen G. Bloids, G. Ruber, and Tetri, G. Saclifer, G. Bloids, again the G. Ruber. So they all are showing a pattern of change during from the dry phase to the wet phase. How they are changing it depends on the stratification and your vertical mixing in the area. So I have done the comparison with our data set with other data set, and you can see that during the Greenland temperature during this time period, at the same time period, 5 to 4 kilo a year, we have a remarkable SST change, remarkable temperature change, and we have total solar insolation, solar irradiation, and only we have done on our we have compared our core data set with it, and it is very well matching, which suggests that it is maybe the change is so much high fluctuation or so much fluctuation is there in the area. It is because of the solar insolation. And then we have done spectral analysis on the G. Ruber data set. This data set is from the Azerbaijan 2019, in which we have got 256 years cycle in the southwest monsoon intensity, which is D-bridge solar cycle. And up to now, what we have seen in many records that we go for only delta 18 records, we prepare the periodicities, but in this data set we have taken the many data sets in this, and then we come to know that 256 years cyclicity is there in the Eastern Arabian Sea. In the Western Bay of Bengal, this is from my record. So in Western Bay of Bengal, we have 418, 165, 139, 109, 97, and 86 years periodicity. This 86 year, 97 and 86 year periodicity is include 77 and 93 years cycle found in foraminifera record of Arabian Sea and of Myanmar respectively. By Legameter, they have given this in their papers, Legameter 1995, Panchan and 2012, and 80 years cycle found in Delta 18 record of HPU Timon launch here, Juan 2014. So the most prominent cyclicity, what we can see, and to have that cyclicity, we have to have very high resolution data set, and then we can talk about the cyclicity. Inferences, delta boron based pH and PCO2 seawater results suggest that CO2 sink during mid-late Holocene. The northeastern Arabian Sea behaved as an abrupt CO2 source during 2 short periods of a strong ENSO activity during 5.5 to 4 kilo a year and 2.8 to 2.5 kilo a year. The northern Indian Ocean was 4 degrees centigrade cooler during Belgium as compared to Holocene. 2 abrupt warm SST excursion from 20 to 19 kilo a year and 17 to 15 kilo a year were noticed during the last glacial period, which would have caused with the variations of a strong northeast winter monsoon wind in the year. A strong southwest monsoon, MIS 1 and MIS 3 we have seen, and the weekend monsoon we have seen MIS 2 and MIS 4 in northern Ocean. Plankton foraminiferal assemblage and isotropic signature records reveal warming during the mid-MIS 4 in the Western Arabian Sea, and the Western Bay of Bengal record suggests the aridification from 5.9 to 3.7 kilo here in Western Bay of Bengal. Stronger stratification was observed during medieval warm period and Roman warm period, as evidenced by planktonic foraminiferal assemblage and isotropic data. For me, it is just take-home message is like more high resolution studies are required to look into the PCO2 and temperature reconstruction and the variation in it from the Indian Ocean to know more about the oceanic processes or the monsoonal processes. Species-specific geochemical analysis to understand the heat distribution through mixed thermocline layer and bottom water height. And last but not least, acknowledgement to the DST BSIP India for funding for this kind of work. Director BSIP Dr. Banda Prasad, organizers of Monsoon Seminar Series for the opportunity to present this series. My collaborators, my PhD guide, Dr. P. Devakar Naidu, and Professor A.D. Singh sir, he was my student's PhD guide. Abjit Majumdar, Dr. Abjit Majumdar, he is here, and BSIP, Dr. Sailesh Agarwal from BSIP, Dr. Ravi Mishra, he is from NCPUR, Goa. Dr. Rajni Panchang, he is from Pune University. Dr. Mayank Shekhar from BSIP. Dr. Pankaj Kumar from IUAC New Delhi. I'm very much thankful to Stephen Blitzer, Henning Kunert, Gavin Foster, and Tom Chalk to really provide the analysis work from their lab. I'm really very thankful for that. And last, my research students, I mean, they are really working hard to get the things done and to make more understanding about the monsoon process. Sayyid Ajuddin, Hidayatullah Khan, Vijesh Kumar, and thank you all.
Great, thank you so much for your talk. I don't know if I can speak for everybody, but you definitely displayed some really fascinating ways and interesting aspects of using forams to study the monsoon and changes in oceanic circulation. So we'll give everybody a moment to think of some questions. And so please, if you could either raise your hand with the little emoji or type your question into the chat, and then we'll call out. Oh, I already see a question from, I believe, Jun Chung Mi in the audience. Would you like to type your question out or put it into the chat maybe? We'll give everybody a
No.
moment.
No, Tara, I didn't.
Oh, sorry. I think you were clapping, maybe. Sorry. Thank you. Well, everybody's gathering their thoughts. I do have a question, and maybe more of a clarification. So it involves the Northeast Arabian Sea as a CO2 source and a sink, which
Yes.
yeah. So I think it's the recent paper that you had with your student as I think as first author.
Yes. Yes.
Yeah.
So, yeah. Yes.
Yeah. Pretty cool. So I guess could you clarify? So the upwelling that causes it to become a source rather than a sink, is that, could you, I guess, reiterate if it's directly caused by the monsoon or kind of indirectly through oceanic circulation? Because I guess, yes?
Yes, it is through the, I'm sure it is through the circulation part, because this, during the ANSO activity that we have this Pacific warm pool there in the western side of the Pacific, and then it's like the heat flux or that comes through the Indonesian through flow to the northeastern Arabian Sea, to the southeastern Arabian Sea, and then it, it gives you that signature. So during that time period, it happens in a very short time period, and that's what the data shows.
Okay, cool. Because I guess, yeah, it seems like there's a really quick like trigger. Exactly. It's like there's like a threshold that you're surpassing in order to get it to be a CO2 source. And
Yes.
and so I'm glad that you're also mentioning that it's over these shorter timescales, kind of the ENSO variability.
Yes.
But you can still pick it up, over from these Holocene records. That's pretty cool.
Yes, that's what I said, that this is one kind of a study. Only on one study, okay, it is good to give your views or write the papers and from where it must have or the reasoning we can give. But I think we have to do lots of work in the Northern Indian Ocean or in the Indian Ocean to understand more and more about it, because the earlier work in the Northern Arabian Sea from the open ocean, it says that because it's from the open ocean, so it says that from 23 kilo a year to 5 kilo a year, the basin works as a source. And if you see one more study by Sushant Naik in 2015 on the same data set, in the CO2 data set. So they say that from 23 kilo a year to 5 kilo a year, they have sink, almost sinking of the CO2, PCO2 there. So it's like that. If we get this kind of abrupt changes in between, so we have to understand more and more about the processes, why it happened in our area.
Yes.
In any area, basically, in the tropical.
Yeah, exactly. And then not only that, one other interesting aspect I found of that part of the data sets that you were sharing with us today was the longevity. So how long these were acting as sources versus sinks. So for example, you documented 2. So one is quite long acting as a source, and then another one is quite short. So I think the 5,000 years is quite long. And then you have the really short one around, I think 2.8 or 3.2.
Yes. 3.2 to 2.8, I believe.
Yeah. So it's interesting that it can both act as a source for quite a long period of time, but also quite a short period of time. So.
Yeah, again, I can say that because we have not, again, I'm saying that we have to look in the processes again in the oceanic. The more we know, the more we get confused. So
yeah, it'll keep you and your students busy for a while.
Yeah.
All the better, right? So,
Yes.
So anybody else have any burning questions? I have another question.
Okay, please.
Which, yeah, so it relates to your work on MIS4. And I just, again, it's a clarification question. And the fact that you were getting this warming that was documented by your planktonic forums. And so you tied that to, I think, solar insolation. Is that basically, that was mostly what it was due to?
Yes, actually, I'm honestly speaking, I'm looking more and more. That is what we have compared our data set with other data sets within the Northern Indian Ocean. They are from the Equatorial Indian Ocean. Why? Because I would like to see if these heat flux or this heat has come from southern part or the southern hemisphere Indian Ocean. I mean, in the form of like, you can say submerged Antarctic water, or from the Pacific warm pool like ITF, through that it is mixing with the NEME and northeast Madagascar current, and then southeast current, and then bringing those things to us, first thing. So, but I have seen in the data set that it is not there in other records from the Equatorial Indian Ocean. I mean, either not from the Mohatidi data set. I think I have done with the Mohatidi data set. So it is not coming out from there. So it means that it is a very much regional scale changes where southwest monsoon intensity little bit picked it up, or the northeast monsoon intensity was little bit lower, because during the glacial time period you have lots of wind coming from the land to ocean, right? So you have always surface cooling, and I mean, and the northeast monsoon intensity, but it is not that much intensified to create the upwelling in the area. But we have seen in our planktonic foraminifera assemblage record that upwelling is there based on, we have seen the G-bloid is there, gluconata is there, and other species, that they all are coming up. They are showing positive response to the upwelling detectability in the area. So that's what I mean. If it is a regional scale change, then southwest monsoon intensity during a particular time period it picked it up, and northeast monsoon intensity was lower during time period. So it is like coupling or decoupling between these two monsoon systems.
Yeah,
that must have happened, because if southwest monsoon intensity is picking up, then only we can say that only triggers the upwelling in the area for a very short time period during glacial time. That is very interesting result. I mean, still I am thinking that to give a very some good outlook for explanation.
Yeah, there's a lot of food for thought for that. And as you said, I mean, you're obviously thinking about all these different dynamics that are happening, and it could be quite localized. And yeah, just because you wouldn't expect that, but you had such a strong signal there. So
yeah, signals is really good.
Okay, any last minute questions burning a hole in anybody's brains? Oh, I see one. I think I saw a question from I think Brajesh in the audience. Did you want to ask your question
in the chat?
Well, I didn't know if the person who raised their hand wants to ask their question out loud or type their question into the chat. Or maybe I missaw that. No, maybe that was a accidental clap, maybe. Or maybe not so accidental. Okay. Well, I would ask everybody to put their hands together, both digitally or here and physically, to give applause again to our speaker for today, showcasing lots of different things that you can do with planktonic foraminifera and all varieties of timescales, and learning about the monsoon. So thank you very much for sharing your research today. And so before the rest of you run away, just remember that we will have another talk next week on Schedule A, which is at a slightly different time, by Bob Reynolds. And I believe speaking about faunal records from the Pakistani foreland basin. So I hope to see all of you next week. And I hope the rest of you have a good rest of your morning, afternoon, or evening, wherever you are.
Yes.
And again, thank you very much for your lovely talk today.
Thank you.
Thank you.
Thank you very much.
Bye, everybody.
Bye.